Okay, so when we left off, we had gotten to the 2-point Arrhenius equation. Basically, this takes into account the change in y over the change in x. And so when you actually look at the equation, it's the natural log of the rate constant for run 2 over the rate constant for run 1 is equal to a negative E sub A over R times 1 over T2 minus 1 over T1. Now, I will say that if you look at the equation in the textbook, it's slightly different because what they've done is they've multiplied through by that negative, which caused these two to rearrange. But what I did is when I wrote the equation, I kept it where it looked very similar to the equation that we dealt with previously, where we were working with pressures and enthalpy, so that the temperature units would be in the same order. Rate constant would simply take over where pressure was, and the enthalpy of vaporization would be replaced by E sub A. As always, R is the dictator. It is telling you what the units of the temperature must be in, and it is telling you what the unit for E sub A must be. E sub A must be in joules, and the temperature unit must be in Kelvin. So let's look at a question. If a temperature increases from 20 degrees to 35 degrees, so we have temperature 1 is equal to 20 degrees Celsius, and temperature 2 is equal to 35 degrees Celsius. If that triples the rate constant for the reaction, so we could say K1 is equal to 1 and K2 is equal to 3, because that would be tripling it. What is the value of the energy of the activation barrier? So it wants to know what is the E sub A for this problem. So again, one of the tricks to this is thinking about what triple means. So again, if you had a 1 to start with, tripling that would be a 3. So that's the easiest way to do that. And then also realizing that that means we are going to have to use R. And so we're going to have to convert our temperature into Kelvin. 20 degrees Celsius is 293.15 Kelvin. And 35 degrees Celsius is 308, I believe. Yeah, 308.15 Kelvin. So using this information, we would have the natural log of K2 over K1 is equal to negative E sub A over R times 1 over T2 minus 1 over T1. Plugging in the information, the natural log of 3 over 1 is equal to a negative E sub A over 8.314 joules per mole Kelvin times 1 over T2, which was 308.15 Kelvin, minus T1, which was 293.15 Kelvin. So we're looking at natural log of 3 is 1.099. Is equal to negative e sub a over 8.314 times a negative 1.66 times 10 to the minus 4, and that's per Kelvin. So doing this math, and multiplying everything through, you get 55042 is equal to E sub A. So our E sub A is basically 55 kilojoules per mole. Basically, to get there, I took the 1.099, divided it by the 1.66 times 10 to the minus 4, and then multiplied by 8.314. That's how I got the 55,042 joules, and that's joules per mole. And so then I converted it into kilojoules. Questions? Yes.
Selling situation like that. And when I get down to my response right before I change it to kilojoules, and I'm off by like, I'm off by like 60 joules just because of rounding errors.
No, so even if you're off by 60, this would come out to be 55.1. So it still rounds to the 55.
So as long as the kilojoule answer rounds closely to the.
Yeah. It basically, I do take into account rounding errors. It has to be a pretty dramatic rounding error for it to be wrong. So, but if it's just a simple, I keep all my digits here, which because I never take it out of the calculator, I kept all my digits here. Yeah, that's going to be where the slight differences come in. And I take that into account. Question. Okay. Then we're going to move on to reaction mechanisms. So we started this chapter just talking about what rate of reaction means. We then use instantaneous rates to calculate a variety of pieces of information associated with a reaction. With the instantaneous rates, we did take into account coefficients of the balanced chemical equation. Because you are looking at a itty bitty time frame. So it matters. But when we actually got into the rate law, we found that, did I actually put all this? Yes, I did. When we actually got into the rate law, the first thing we said is, okay, the general form of the rate law is rate is equal to K times the concentration of a reactant A to its order times the concentration of reactant B to its order. As you saw yesterday in lab, when you're writing the rate law, the only thing that actually goes into the rate law are the reactants. Now, these orders, this M and N in the general rate law, cannot be determined by the coefficients of the balanced chemical equation, meaning you don't pay attention to coefficients with rate laws. So again, you paid attention to coefficients with the instantaneous rates, but you don't pay attention to coefficients with the rate law. Instead, with the rate law, you actually have to determine the order experimentally. And as we saw yesterday in lab, there are two ways to do that. There is the integrated rate law, and there is the method of initial rates. What we're going to do now is we're going to talk about how does this rate law, how come the rate law doesn't take into account the coefficients? And the how come is based off of the reaction mechanism. Specifically, the rate determining step or the slow step of the reaction. I'm trying to let people catch up with me that are writing it down. So again, instantaneous rates describe what occurs in a reaction in a very short period of time. They do take into account the coefficients of the balanced chemical equation. But when we get to the rate law, the general form of the rate law is always basically the same. Its rate is equal to the rate constant times the reactant. It's always just the reactants. It's never products. It's never intermediates. It's just the reactants raised to their order. And those orders can be determined experimentally. What we're going to do today is we're going to look at why these orders are not necessarily related to the coefficients of the balanced chemical equation. So when we write a general reaction, A plus BB goes CC plus DD. This is the reaction you're used to seeing, where these reactants go to form the product. But we have never said that that reaction occurs in one step. Reactions can occur in a series of steps. And this series of steps is called a reaction mechanism. Now, I'm going to introduce a lot of different terminology, and then I'm going to apply that terminology. But one thing you have to know about reaction mechanisms is that a reaction mechanism is an educated guess as to what's occurring in the reaction. It is that educated guess is based off of observations through various pieces of instrumentation. But it's still an educated guess as to what's going on. So the reaction mechanisms is a series of individual chemical steps by which the overall chemical reaction may occur. Here, the overall reaction is H2 plus 2 ICl goes to form 2 HCl plus HI. We have made an educated guess that this is a two-step reaction mechanism. And if you look here, in the first reaction, you have an HI in the products. In the second reaction, you have an HI in the reactants. Because they're on opposite sides of the equation, they do cancel out. And therefore, if you add up what's left after canceling, you can see where the overall reaction comes from. This is kind of like Hess's law. Okay. So now some terminology associated with reaction mechanisms. And I'm going to refer to many of the things that just went on in this example. First of all, those individual steps in the reaction mechanism are referred to as elementary steps. In the previous example, I was able to eliminate the HI. The HI is referred to as an intermediate. Intermediates are going to be substances that are products in early steps that are later used up as a reactant in a different step. So another term that we haven't introduced is this concept of molecularity. When we are developing a rate law, we're essentially describing the molecularity of the slow step. Now, molecularity can be described as a unimolecular reaction. If it's a unimolecular reaction, there is only one reactant. You can have a dozen products, but there's only one reactant. So again, this is about the number of reactants. If it's bimolecular, it's going to be two reactant particles. You could have two of the same particle, or you could have different particles. What do these molecularities mean? Well, in a unimolecular step, if you have a unimolecular step, it means that something has to happen to one reactant molecule. Typically, that is some sort of torque that has occurred to the rotation of the molecule in order to separate the molecule. It could be adding temperature and therefore adding energy to break a bond in the molecule. But it is about just one molecule that has to undergo some sort of transformation. When you talk about a bimolecular, it means two molecules must encounter each other. They have to encounter each other with the correct energy, the correct orientation to get the reaction going. Termolecular is a term used if there are three particles, three reactant particles. Termolecular reactions are actually very rare because the termolecular reaction means you have to have three molecules interacting simultaneously with the correct energy, with the correct orientation. All of that has to occur in order for the reaction to happen. And therefore, termolecular reactions are actually quite rare. Most of the time, you're going to see a lot of bimolecular reactions because this is probably the easiest. But unimolecular also occur. So again, when you have that series of chemical steps in a reaction mechanism, those individual chemical steps are called elementary steps. When you have something that is made in an early reaction that is later used up in a reaction, then that is the intermediate. And then the idea that a reaction may not resemble the coefficients, the rate law may not resemble the coefficients, comes down to the molecularity of the rate determining step. Now, while the rate law for the reaction cannot be determined by stoichiometry, we can determine the rate law of the elementary steps using stoichiometry. The rate law for the overall reaction cannot be determined from stoichiometry. But the rate law for the elementary steps can be determined by stoichiometry. The rate law for the overall reaction is going to be determined by the rate determining step, which is also known as the slow step in a reaction mechanism. I'm introducing the terminology because I'm going to be using the terminology. And it is something you need to be familiar with when it comes test time, because I don't typically have questions where you are matching definitions. Instead, I have a question that uses the term, and you have to know what the term means or you're not going to know how to answer the question. Questions so far? Okay. Now, as I said, reaction mechanisms are educated guesses as to the process by which a reaction occurs. So how do we know if our educated guess is a valid option? In order for it to be a valid option, it must meet two criteria. The first criteria is that the reaction mechanisms, the elementary steps, must add up to the overall reaction. If the elementary steps do not add up to the overall reaction, then we know it's not a valid mechanism. The second thing is that the rate law of the rate determining elementary step has to be the same as the rate law for the overall reaction as was determined experimentally. So again, you have to meet both criteria in order for this to be a valid mechanism. The elementary steps have to add up to the overall reaction, and the rate law from the rate determining step has to be the same as the rate law for the overall reaction that was determined experimentally. Okay. Time to illustrate all of this. First of all, the overall reaction was nitrogen dioxide plus carbon monoxide goes to form carbon dioxide plus nitrogen monoxide. That had a rate law that was determined experimentally. As rate is equal to the rate constant times the nitrogen dioxide concentration squared. A mechanism was proposed where the rate determining step was the first step in the mechanism. The rate determining step is bimolecular. because it has two reactant molecules. The fast step is also bimolecular because it has two reactant molecules. Now, the first criteria to know whether or not this is a valid mechanism is that the reactions, the elementary steps, must add up to the overall reaction. When I look at this, on the reactant side, I have two nitrogen dioxides. Later on the product side, I have one nitrogen dioxide. So one of my nitrogen dioxides is going to cancel out. On the product side, I have a nitrogen trioxide. And on the reactant side, I have a nitrogen trioxide. So the nitrogen trioxide is going to cancel out. What is left when I cancel out like molecules is nitrogen dioxide reacts with carbon monoxide to form nitrogen monoxide and carbon dioxide. So this reaction mechanism meets the first criteria. In this reaction mechanism, the intermediate is nitrogen trioxide because the nitrogen trioxide was created in an early reaction and was used up in a later reaction, meaning it was a product in an early reaction and a reactant in a later reaction. We can't say this is valid yet because we still have to meet the second criteria, which is that the rate law of the rate determining step must produce the rate law determined experimentally for the overall reaction. Now, the nice thing is when you're talking about a rate law for an elementary step, it is related to stoichiometry. So this is rate equals K times the nitrogen dioxide, and that nitrogen dioxide is squared because you have two nitrogen dioxide molecules. So again, when you're dealing with the rate law of an elementary step, the rate law is related to stoichiometry. And so you can simply write the rate law based off of the stoichiometry. Now we can say, yes, this reaction mechanism is a valid reaction mechanism because the overall reaction is the same and the rate law from the reaction mechanism is the same as the rate law of the overall reaction that was determined experimentally. Questions? Now, what does this reaction mechanism look like in an energy of activation diagram? first of all, when we develop the energy of activation diagram, we're talking about an increase of energy on the y-axis, and we're talking about the reaction progress on the x-axis. Since this is the reaction progress, moving from left to right, that means that our reactants start out on the left, and we ultimately end with our products on the right. Now, if you look at the previous reaction mechanism, it was a two-step mechanism. So that is why there are two humps to represent a two-step mechanism. If you look at the previous diagram or the previous reaction mechanism, the first step was the slow step. When we say it's the slow step or the rate determining step, what we're describing is the energy of activation. If it is a slow step or a rate determining step, that means that that step is going to have the most dynamic, the biggest energy of activation. So since our first step was the slow step, we would expect the first step's energy of activation to be the larger energy of activation. Now, there are a couple of other things in this diagram. First of all, the top of the pump is called the transition state. And the trough in the middle is where our intermediates are. Now, one thing I want you to note is when you're determining the energy of activation, it always starts with wherever that hump begins. So on the first diagram, that energy of activation starts at the level of the reactants. But on the second step, it starts at the level of the intermediates, because it's always going to start where that hump starts. So looking back, basically, folks, this would be our two NO2 molecules. They would go and something has to occur so that they're in their transition state between being two NO2 molecules and the next thing. The next thing being an NO3. Let me write it under the word. And an NO. The NO3 then undergoes a transition, and you ultimately wind up with and it reacts with carbon monoxide, and you ultimately wind up with the products of nitrogen monoxide and carbon dioxide. This transition state here is where the nitrogen trioxide is reacting with the carbon monoxide. And something's going on between those two molecules at that point before it tips on over to form the final products. In this case, this is a exothermic reaction. Because the products are lower in energy than the reactants. So it technically should have a negative delta H. So again, this energy of activation diagram is telling the story from that reaction mechanism we just looked at. It has to, according to the reaction mechanism, it has to occur in 2 steps. We have 2 steps. According to the reaction mechanism, the first step was our slow step, meaning it has to have a much larger energy of activation. Reaction progress, you always start with the reactants. They go up to the transition state, meaning that something is going on at that point between those 2 reactants. Something is going on, but we haven't gotten to the intermediates until the bottom of the trough. The intermediates being the product of the first reaction, reacting with the next substance in line. Then we go up. We have the reactants doing something that ultimately form our products of the reaction. Yes.
The intermediates, if like we're asked to like label them, I thought the intermediate was only the one that doesn't reappear in this last step. So we keep like the and then.
Okay. So this is thank you for that question. This is where the intermediates are present. It's not just intermediates, it's where the intermediates are present. So let's look at an example. And I want to give you a moment to try and work through this. You can't do the last one until I go to the next slide, but we can at least see how much you picked up from the demonstration in this example. So it's giving you nitrogen dioxide plus chlorine goes to form ClNO2 plus chlorine atom. The chlorine atom reacts with another nitrogen dioxide molecule to make another ClNO2. The first step is the slow step. The second step is the fast step. You're asked, what is the overall reaction? To identify the intermediates in the mechanism. To identify the molecularity of each elementary step. And to determine the predicted rate law. We'll look at this last question here in a minute. The first three should have been straightforward. Number 4 shouldn't have been too bad. What is the overall reaction? You add the two reactions together and you'll notice that Cl gas disappears. What's left is 2NO2 gas plus Cl2 gas goes to make 2 ClNO2 gases. The intermediate is what disappeared. It's the Cl gas because it was a product in the first reaction and it was a reactant in the second reaction. They are both bimolecular because both elementary steps have 2 reactant molecules. The rate law is dependent upon the rate determining step and can be determined stoichiometrically from the rate determining step. Therefore, the rate law for the rate determining step is rate is equal to K times NO2 raised to the power of 1 times Cl2 raised to the power of 1. And that would be the predicted rate law. Questions about those 4? Now, on the next slide, I'm going to show an activation energy diagram, and I want to know if it's a valid activation energy diagram. First of all, let's answer the second question. Is it valid? I see one head shake. Who says it is valid? Who says it's not valid? Who wishes to not say? It is not valid. Because which step has to be the slow step? Step 1. You compare those E sub A's. The slow step did not occur in step. That is terrible. It's not even a valid energy of activation diagram. Why? Because we have to go from the bottom all the way up. And we need to compare that with that one. This is what happens when I make slides at 5 a.m. This is definitely not a valid energy of activation diagram. Looking at those energy of activations, they're telling you that the second step was the rate determining step, which I disagree with. But if the second step had been the rate determining step, it would have been wrong. Because the rate determining step was the first step. A is the reactants of step 1. B is the intermediate plus the reactants of step 2. And C is the products. Questions? Okay. It's easy if the rate determining step is the first step in the reaction. Because all you got to do is look at that first reaction and determine the rate law for that elementary step, and you have the predicted rate law. It is more challenging. If the first step is not the rate determining step. It is going to be more challenging when that first step is a fast step. It is more challenging because that means that we're going to have to do some manipulation of the equation, because ultimately our rate laws can only contain reactants. So let's look at an example of how we go about it. Here you have two nitrogen monoxides reacting to form dinitrogen dioxide. This occurs in a fast step, meaning that the forward reaction and the reverse reaction are going at the same speed. So you have a forward reaction and a reverse reaction. Once the dinitrogen dioxide is formed, that reacts with hydrogen to form water and dinitrogen monoxide. And then the dinitrogen monoxide reacts with another hydrogen to form nitrogen and water. The overall reaction, the dinitrogen oxides cancel out. The dinitrogen monoxide cancels out. And you're left with, making sure, 2 nitrogen monoxide gas plus 2 hydrogen gas goes to form nitrogen gas plus 2 water gases. The intermediates for this reaction are dinitrogen dioxide and dinitrogen monoxide. They are intermediates because they are formed in a prior step and then used up in a later step. Now the hard part is getting to the rate law. The predicted rate law is going to be the most challenging part of this question. Why? Well, first of all, the rate law is dependent upon the slow step. So we write the rate law for our slow step, and we get rate is equal to K times the hydrogen times dinitrogen dioxide. But our predicted rate law cannot contain intermediates. So it's our predicted rate law cannot contain dinitrogen dioxide. So the question is, where did that dinitrogen dioxide come from? And it came from this first reaction. So let's see how we can use this information. So again, we wrote the rate law for the rate determining step. And that was rate is equal to K times H2 times N2O2. But we're going to have to go back to this fast step to figure out how to eliminate the N2O2. Now, when we say it's a fast step, what it means is you have the forward reaction and you have the reverse reaction. We can say the rate of the forward reaction is equal to its rate constant times NO squared. And we can also develop a rate of the reverse reaction, which is equal to its rate constant times N2O2. Now, because this is in dynamic equilibrium, meaning the rate of the forward reaction equals the rate of the reverse reaction, that means that K of NO squared is equal to K of N2O2. Now, to help keep these K's constant, I'm going to call it the K of the forward and the K of the reverse, but you're going to see them just disappear here in a minute. Now, if we divide the right-hand side by K of reverse, we got to do the same to the left-hand side. On the right-hand side, that K of reverse is going to disappear. On the left-hand side, these K's are simply going to be combined to form K is times NO2, or NO squared. That's equal to our N2O2. We now have something we can plug in for N2O2. So the rate is equal to the K of our hydrogen times the K for our N2O2, which was NO squared. Now again, these K's are simply going to combine. So you have rate is equal to K times H2 times NO squared. That is the predicted rate law for this reaction. Yes.
You only do this if the first one's in dynamic equilibrium.
The question is, can you only do this if the first one's in dynamic equilibrium? The answer is, if the second step is slow, the first one will always be in dynamic equilibrium. So yes. So again, the trick. You write the rate law for the rate determining step. But because you're not allowed to have intermediates, you have to figure out where did that intermediate come from. That intermediate came from the first step, which just happened to be a fast step that's in dynamic equilibrium. What that meant is we could write a rate law for the forward progress and a rate law for the reverse. And those two rates would be identical. Since the rates are identical, that means that the Kf of NO squared is equal to the Kr of N2O2. But we needed just N2O2. So we rearranged this equation to solve for N2O2. Now, folks, all these K's, they're going to combine to form one K, because as we've seen from the rate law, it's always rate equals K time. So they all just combine to form one rate constant. So once I had the N2O2, I plugged that in for N2O2, and I simplified it. And I got the rate law for this reaction. I'll pick up with one more example on Thursday. We'll actually do and also we'll look at the energy of activation diagram and determine if it's valid. And then we'll go on to catalyst and start talking equilibrium. Yes.
Graphs.